Okay, so welcome everybody. Tonight we're going to continue with, I think, our fourth meeting on Mamba. And tonight we're going to dive into the code a little bit. It was fairly hairy to get through the code, but hopefully we've reduced it down to some figures that'll make it more digestible. So I will start as soon as Jerry lets me share my screen.
Oh, I have to let you share your screen?
Yeah.
One participant. Where do anybody know where I let you?
When Roger, you try to share, does it send you a notification?
I think at the bottom next to share screen, there's a little like caret triangle thing.
Yeah,
and I think that's where you.
It just says
Host disabled participant screen sharing.
Ooh.
Yeah, so there's a setting. There's a setting somewhere. I think you click just on the settings, and then you just say.
Give it a shot, Roger.
Okay, I'll try again.
Looks like it's working.
Huh?
Screen share, and we'll go here. We might switch over to VS Code a little later, but we'll start with this. So how's that screen-wise? Does that work out okay?
Looks good, man.
Okay.
Do you want to click on the slideshow on the top right?
Yeah, you might want to click on the slideshow.
Oh, but then I can't navigate. There's another one. There's a.
Okay, yeah. Your screen looks really huge to me. Anybody else? It looks.
Yeah, you see that arrow, Roger, below share, there is an up arrow. Below share? No, the right to it. Yeah, click that one. That will make it slightly more big. And then if you want to minimize
there's a mode we can. Yeah, there's another mode where you can share it. But if you can see this, then that's fine.
Well, it's wider than my screen, and I'm the one recording. That's kind of a problem.
Okay. All right. Well, then I'll make it a subscreen. How's that work?
Yeah, that works. Yeah.
How's that?
Yeah. Okay. We're good there.
Okay.
Yeah. Perfect, man.
Okay. Okay. So, yeah. So what we're gonna do tonight is go through. There's some pictures. We took some figures out of the paper. Tried to expand them a little bit. I've kind of brought some of the knowledge from. Thank you to Jason and Dave who joined. Diving through the code and tried to pull some of that back up into a diagram that we can look at. So we'll go through and talk about it from kind of a system architecture diagram perspective. And then we'll dive down and just look at the code. And it should be pretty quick once we're oriented with the architectural picture. And then there was a couple questions that we had that I thought we'd go into a little bit, although there's some we have answers to. I think some were just a little too deep. We might want to have another talk later on about Hippo. So does that look like a reasonable agenda? Any questions anybody else had that top of mind to answer?
Looks good.
Okay. Okay. So figure 3 in the paper, this is the figure 3 showing the sequence state machine in the center and wrapped around with some additional layers, including one thing we hadn't really talked about, a convolutional layer. That's convolution through time, I believe, and some expand, contract things. And this one ends up being kind of interesting, also not talked about, that I saw kind of a gating channel that comes in after the state machine. So the second diagram, we spent a little bit more time, I think. Ted had this up on the screen a few times. That showed where we had, once we'd discretized the A and B and C matrices, or I guess just A and B, how they fit into a state machine where you've got a prior state coming in, you're multiplying it by a state transition matrix, you're adding in something from the input through the B matrix, and that gets added into the state. In here, it shows it is added before A, which is misleading because it actually gets added after A. But and then that flows out, and meanwhile you pull out using the C matrix. You project that hidden state into some sort of output. I think the main thing they were trying to communicate here was their hardware optimization, where they were leaving some things in the SRAM and kind of sweeping through the sequence, calculating the matrices that they needed on the fly. Again, we've talked about it before, but in Mamba, one of the things that they did is they allowed B, unlike what was it, S4, they allowed the B and C matrix to be modified. So it's not constant throughout the entire sequence, it's modified, and in fact modified by the inputs, input to the model. And another one is that this delta T thing where they modulate the discretizing time step. And it has an interesting effect. And we'll dive into that a little bit too, I think, later on. Okay, so what we're going to do is try to integrate these two pictures into one. So this part's kind of through time. This part is, depending on what you think of as the input or the output. If you think of the input as an entire sequence, yeah, I guess it still wouldn't quite match up. This is more akin to a single token flowing up through the module. And typically that would flow into additional layers of the module. Whereas this larger diagram is more through time, through the sequence. So what I'm going to do is try to pull those two together, bring that one that shows the state going through, pull that down into this lower diagram. And that looks like, why is that? Oh, I don't know why that didn't draw. This must be something about presenter view. Okay, so this is my attempt to do that. And I'll walk through this and then we'll go look at it a little bit more in terms of dimensions, and then we'll dive into the code. So the first thing is, well, let me ask, any questions so far? Okay, so feel free to speak up and just interrupt me if anything comes up. So they have this, the model dimensioned input coming in down there at the bottom. So what I've got now is I've got the input comes in here and the output there. So this would be, you know, the current tokens, and that'd be next token if we're doing like a sequence prediction. We've got through time, we've got the state in this red line where the prior state comes in, is going to be modified, and then it's going to flow out to the next state. And we've also got something, I'm pretty sure we concluded that this convolution layer is actually a convolution that occurs through time as well. So that looks at, I think the number we found was 4 different tokens, essentially 4 different time steps, if I could use that term, 4 different time steps, and runs a convolution on that. And actually, I don't recall if we looked to see if that was just a full convolution or it was per dimension.
It's a 1D convolution.
1D. Okay, yeah. So then it should be per channel or per dimension of the input.
That's right. So it's a 1D convolution, and also I think number 4 is for the toy implementation or the default value, if you may. I shouldn't say toy, but yeah. I'm assuming it can be overwritten. It's a configurable parameter that can be passed to the instance of SSN.
Okay, so that's it. So we've got 2 things here that are flowing through. The convolution flows through time, the state flows through time. So there'd be the prior token would have a similar stack over here. The next token would also have a similar stack over here. And then going from the bottom to the top, we've got the input. So this would be like, if it was a language model, it'd be the embedding of a single token, and it would be flowing up through this, and the output then would probably be going to another layer on up until you got to the top and projected back into token space.
Yeah, and this is per layer.
Yeah, so this is one view. I'm gonna a little bit later we'll blow it up and you can see how like the pieces would fit together with layers. But this is one layer, one token. So I'm following kind of the approach that Ted did with the transformer. I'm trying to, and that we explored like one transformer, but then looked at it from the perspective of how does it fit in when you're training? How does it fit in with all of the tokens in the sequence and all of the layers in the model? But we're going to dive into just this one token, one first layer first, okay? Okay, so we've got the model coming in, and then we do a projection from the model space into a higher dimension, run that through the convolution, which it will run a 1D convolution with its neighbors. We run through a non-linearity, I think that was a Silu. And then that goes into two different locations. So the biggest one is it goes into this projection. The projection takes the input and generates the B matrix, which will be used for mapping the input tokens or the input dimensions into the hidden dimensions. It also generates the C matrix, which will map the hidden dimensions back into the internal dimensions, so from a wider space down to more narrow space. And then the other thing it does, it at a lower rank, and I think it was the default was like 16 or something like that. They output a vector that is then runs through a projection, and this is for the DT. So this is a part that was kind of a stumbling block for me, because when I thought of digital systems, I thought of generally you were probably measuring an analog system, continuous system, and maybe outputting to something that would have a continuous system. But usually I thought of the sample interval as something that is constant. And so I was struggling quite a bit with what does this mean to learn the parameters around the DT. But
hey, Roger.
Yeah.
If you want, I can jump in. I think I can help a little with that.
Okay. We can get some, can you jump in a little later? We'll do that. I think I
Sure.
have another place where we talked about the DT stuff. But what I was wanting to communicate here was just that the mapping to the time step is actually a learned projection from, it's kind of two layers. It projects into one space, small space, and then back out into this inner dimension space. They run it through a soft plus, and then do an operation, basically multiplying the A matrix by the output of that, as well as the B matrix. So let me follow actually I'll do the A side first.
Hey Roger.
Yeah.
What is the soft plus operation? Is that soft max addition or what? What do we go?
I didn't look up soft plus.
Okay.
Does anybody know? Does anybody look that up?
It's just a detail. I hadn't seen it. Hadn't seen it before. So
Jerry, just think continuous ReLU, curvy ReLU.
Okay.
Right,
so it's pretty similar to JLU, Swish, and all the other ones they're using.
Okay. All right. Well, that's kind of what I was thinking, but I just want to make sure. Thanks.
So that's interesting, Ted. So it's interesting that so here was the, I'm not sure what SILU, I think these were SILUs. But this is soft plus, so they ended up using different nonlinearities, huh?
Yeah, I think this one is not as critical, so they used one that's faster to compute. Not sure.
Okay.
Well,
Okay.
that seems to be a theme, right? That these guys are trying to do everything they can to make this fast, so.
Especially in here.
Yeah, especially in there. And this is,
Yeah.
back to recalculating, even though rather than fetching from memory. So,
Yeah.
Okay.
So I'll start over here then. So the two parts are going to be the A bar and B bar are kind of maybe the two most interesting, but starting with A bar. So there's a couple things here. They start with the S4 diagonal. So that's if I'm understanding, it's more or less the diagonal elements of the hippo matrix, not transition matrix. Ted, I don't know if it's basically, I think I saw this. It's just the diagonal is 1, 2, 3, 4, n up through n. They initialize it, and I'm not quite sure that when we look at the code, if somebody else has a different read on it, it can update us. But basically, they construct a matrix that's got diagonals 1 through n, and then they take a log of it, and that becomes this A log matrix, and that it looks like they use to initialize a parameter. So they learn A log, oh, excuse me. Yeah, A log is a parameter, which is a little different because I thought A was fixed. But they mark it clearly as a parameter. So I don't know, maybe they use it in fine tuning later on or something like that, but it's initialized with the same diagonal that S4 would have used. And what's interesting is I've seen this done somewhere else in a parameter as well, where they want this A to be always positive. So what they'll do is they'll set the parameter in the log space, and then they'll take the e to the x, so the exponential function of that at runtime. So that guarantees that it's going to be a positive number from 0 to infinity. A log is unconstrained. It can be any value. The exp of A log will always be positive, and they want actually in this case always negative, so they take the negative of that. That then becomes the A. So this is the continuous domain A. Once you have that, they do the process to do the discretize the A to come up with the A bar. They multiply it times the delta T, so the output of the soft plus. They multiply it by that, and then using the, if you look at the paper, let's see, I think I have the paper here. If we look at the paper where they do this thing, this is the 0 order hold that they do. So we're going to take the delta times the A matrix, and that's the parameterized A bar, discretized A bar rather. So that's how they calculate A bar. An interesting thing is, from what I could follow from the code, B is not actually, here they say they use B to be this equation. From what I could tell, they just are doing this part of it. It's kind of like they threw away the other part. And I don't remember reading that, but that's what the code seems to show. Any questions, comments there? Okay, so in this equation, then is again, this is the 0 order hold. This is how we go to a continuous to a discrete set of coefficients for the differential equation. And 0 order hold, I think Jason, you would, or no, actually it was your buddy that pointed out that for very small delta, this should actually equate to the Euler equivalent mapping. and hypothesized that the zero order hold maybe works better when delta t is larger. Ted, was there anything more? Well, actually, this is the part where this delta t actually can act as a steering. Either you could view it as a time dimension where when you're doing discretizing the A matrix, the continuous matrix, or because there's a multiply on the A side and what is it, that this minus I on the right hand side, you could think of it as a steering between the input, weighting the input more heavily and the continuing state less heavily, or vice versa, way that if you imagine this as being delta as being 0, then let's see, A bar should be 1, which means you pay full attention to the history, the existing hidden state, and what would be if delta was small over here and B was delta B, that would mean you pay 0 times B, so you pay no attention to the input. So when you talk about converting to discrete form, delta t would be a time, but the way in which they're modulating it actually seems to end up having the effect of steering towards either retain your state or update your state.
So one quick comment I wanted to make, Roger, is
Sure.
figure 1, which you had in your slides, but it's also at the top of the screen right now.
Yep.
You'll notice that towards on the bottom left is your quote unquote input. I know it's gone through the other stuff and whatever, but internal to just this part of it, that's your input. Okay. And then the blue blocks, this tiny little blue square to the right of that, that's your projection matrix, where basically you get to do things. But what you'll notice is that for the 3 lines that come out of that projection matrix, everything has a subscript T. Okay. And so if you're talking like a time series, then you would think of T as time. If we're just talking about like a language model, then T really just corresponds to your token positions. That's your sequence positions. Okay. So I just wanted to clarify, because you mostly haven't been mentioning T when you talk about B and C, but you have been mentioning T every time you talk about delta. And so delta sub T is not the same thing as in calculus where you have dt. So if you have an equation in blah de blah and you integrate it and you say blah de blah dt, and I'm going to integrate it like by t, that's not what delta t means. Okay, I don't fully understand all the math, but I think the easiest way to understand delta is the last thing that you just said. A delta close to 0 means ignore my input and mostly maintain my hidden state as is, because e to the, delta a or whatever, right? Or no, the other way around. But anyway, the point is, if you delta big or small will tell you how much you're forgetting your previous hidden state. And if you forget your previous hidden state, then all you're left with is your new input. So if you think about like an old, RNN or LSTM or something like that.
Hey, Ted.
Yeah, so go ahead.
Yeah, so would this be, let's say we're going down the road and we decide that, the input has changed or something like that, and we don't really care about what was before? Is this how you would dump that, or what is this forgetting? How is that working?
So it's complicated, all right?
Of course.
But the general gist is that you can imagine that when you get to the end of a sentence, when you get to the end of a paragraph, when you see a really common stop word like the, whatever, that you're likely going to you're going to keep more, sorry, that was backwards. So the end of a sentence, end of a paragraph, you would think you're going to forget a lot more of your hidden state because you're starting something new and you want to put more emphasis on your input. The opposite case would be if you see the word the maybe you're going to keep more of your hidden state because there's not a whole lot of information being added when you see the word the again.
Okay. Yeah.
Does it
Okay.
mean that
Right.
delta is a vector, but it contains the variables small enough that it considered exponential delta a minus I as delta a? Is that right? So delta a inverse delta a is multiplied by delta a is 1 I.
Right. So I think you're right on it. So when you look at the transform of your continuous in the let's say Laplace transform or whatever transforms you have that you look at there, and you try to get the Maclaurin series for that, you look only at the first term, and that is the delta t that I think it is trying to derive here, which goes into your equations. I'm assuming that's what it is trying to capture here for each dimension.
So regarding that, it's not attention, but it emphasizes on a specific words, right? Like nouns, like verbs. So if the delta, which they are small enough, if they are larger, it means that the effect of the word is higher, and it ignores the words before that, or vice versa.
That I will defer to what Ted said, because the interpretation of that is exactly what Ted was describing. I mean, I'll think through it and maybe give you the same answer that Ted would give you much faster on the interpretation side.
Right.
Yeah, so S4, the previous state space model, did not have this delta, and the delta didn't change depending on what the next token was. Okay?
Actually, it did have a delta. It just didn't have, it had a delta t. It just didn't have a delta that varied with time.
Okay.
So in S4, yeah, S4, go ahead.
So the key, so we do want to remember that most of what we call like the equivalent of attention, the equivalent of this smarts over time, is being handled by the hidden state. Okay,
Right.
Delta's not doing the heavy lifting here. The heavy lifting is being done by the hidden state. However, in Mamba, having the ability to modulate delta a little bigger, a little smaller. So as you pointed out, a delta, if e to the delta times a is close to 1, that means a bar is going to basically be very close to a. And then that minus I is going to be very close to 0, right? So if you have all ones and you subtract I, you're going to get something very close to 0. So e to the delta a close to 1 means a bar is big and b bar is small. And then the other way around, if that number is very small, then b bar becomes bigger. So I forget the exact words the authors use, but they somewhat loosely say you can think of delta akin to the forget gate in an LSTM. Okay, I'm not saying it works exactly the same way, but basically, in addition to your hidden state and all the heavy lifting it does, you're giving it the model a little bit of a boost because you now are sort of like adding a forget gate on top of the state space model dynamics.
Isn't it the same concept as attention in a transformer, or what's the difference between them?
For me, it's hard to compare because attention is so explicit. You can see what it's doing. There is no hidden state in a transformer. You have access to every token that ever came before you, okay? And you explicitly calculate this QK similarity computation to decide which tokens you're going to pay attention to. Now, why that similarity is useful, like, right, that gets very complicated and whatever, but you can see at least mechanically this layer 5 of the transformer on token position 10, it attended to word, number 3, which was boy, and it gave it really high tension. So you can see that. It's not as obvious to me how you would explain that, like, in a given token position, the hidden state then caused you to pay attention to, 10 tokens ago. It's not as obvious to me how you would kind of have that intuition.
So it's kind of with a transformer, you basically remember everything, and you can access everything each time you predict the next token. Whereas in a state machine like this, you make the decision of what do you put into your state and what do you take out of your state. And then the state is captured in that HT type of thing, and in a presumably more compressed form.
Right. So we could imagine that, like, for example, if the word ball has a query that has a very high score with a key for the word boy. So anytime you have the word ball, it's going to attend very highly to the word boy that appeared before it, okay? You could, in this hidden state, have some similar representation that once you see the word boy, you could say, hey, by the way, if you see the word ball later on, I want you to pay attention to me. But it's not as obvious to me how you would just explain what is being compressed into the hidden state. But that's the job of it, is to express those kinds of relationships somehow.
So the one thing I wanted to say, Ted, you're thinking of the delta as primarily a steering thing. I do want to point out it's kind of a duality of it's a selection thing as well as the transformation from a continuous to a discrete form. So you would see this, it just would not be modulated. The delta would exist in the S4, for instance, it just would be constant for all of time, for the entire thing. And I think, I haven't completely figured this out, but when you ask the question of how can this be, why do we get rid of the vanishing gradient? I think part of it is that this idea that in these state space models, the model is actually continuous, even though what we work with is discrete, and we can sample the continuous functions at whatever resolution we want. So depending on the sequence length, we can sample it at different rates. And so that's why this ability to convert from continuous to discrete is important. And I think they said also that the matrices don't change, the values don't change based on the sample frequency. It just, they are represented in the continuous domain. So it is a duality. It serves as both functions, conversion from continuous to discrete, as well as the steering between remember or forget or add new state. Thing.
Hey, Roger, did you say the sampling is fixed or is it variable?
In S4, it is fixed.
Okay.
For all the tokens have the same value. In S6, they've allowed the A and not A, the B, let's see, the A bar is updated, it is different for every token because the delta is different for every token.
Oh, okay.
Also, B and C are generated for every token, so they're different as well. So it's kind of actually ends up being all three are flexible. Yeah. It's just that A is flexible in a certain way.
Well, it looks like the thing there where they talk about discretion, it looks like A is only a function of what delta, and then A itself, and B has got delta A and B. So
yeah. And again, this is just the way you convert from continuous to discrete. I think if you did just an Euler implementation here, it ends up being, it would probably still work. This I think is just a different way, one of the ways that you can convert continuous to discrete. And I think it's that modulation of the delta that controls the steering. I could be wrong there, but I think that's correct.
Okay, thank you.
Okay. Okay, so let's see, where was I on here then? So we went through generating A bar. B bar is kind of interesting in that you generate this delta through this DT projection. And then you do an operation between that and B and generate another one. There's two different ways that this is expressed, but basically the continuous the continuous form is generated, and then they run it through the discretization step to get B bar, and then B bar is multiplied by this internal state to get what the update to the state vector, the amount to be added to the state vector. So here you're controlling how the old state flows through, and then here you're deciding how much and how to add state to that.
Hey, Roger, can you put it in presenter view again, please?
Yeah.
I actually had a comment or a question. And tell me if this is right, that when we talk about discretization, maybe outside of this context, we're talking about the idea of like continuous time, where you would sample something in a computer where you're discretizing it in time. And is it right? My understanding anyway is that when we're talking about discretization here, it's not quite the same as that. It's related more to that discretization is more like how much you're going to weigh your input versus your existing state. Is that right? That statement?
I think it's both. It clearly has the effect of steering, but where you didn't have this selective nature that S6 has, back in S4, you still would have had that same matrix and that same transformation. It's just what you would do is, instead of having X projected into DT like that, you would have a constant for all tokens. So this would not be a function of the input. This would just be a constant for the entire sequence. And I think it'd be based on the sequence length.
So Roger, can you show the equations again for a second? So I think it's equation 1 in this paper, but I can't remember if they number them differently. Okay, 1A is what he calls it. So if you look at equation 1A, and if you can make it a little bigger, that's great, Roger. Otherwise,
where's 1A? I see the 3, I don't see the 1.
No, sorry. It's that block that has all 6 equations. You had, right there, at the beginning.
It starts with 3. Okay.
No. If you look, it's 3 columns. There's a 1A.
Oh, okay. Gotcha. Yeah, that 1A. Gotcha.
So let's simplify equation 1A and drop the B part. Okay. So if the equation was just H prime equals, and let's not even do multidimensional. Let's just have this be scalars. Okay. So H prime equals some constant A, which is just a number. It could be like 1.1. Okay. Times H. Okay. So if the first derivative equals a certain multiplier of your state, then basically this thing is not going to grow linearly, right? Because as H gets bigger, the effect of multiplying it by 1.1 is going to continue to get bigger. And I'm not sure if I've got the math right, but like going back to like high school math where they talk about like compounding interest or like multiplying bacteria. If you remember, you can convert that to a formula that looks like some constant, e to the k times t. All right. And that's actually what you have on the left of equation 4, is e to the some new constant delta. That's our k. All right. And since we're always doing one time step, you don't need a t in that equation. So discretization very much is, discretization, I think of it as integration. So when I was talking about it in previous weeks, I tried to say you have equation 1a, and that's continuous, and you want to know every 30th of a second, how much is my hidden state H going to change?
Mm-hmm.
You need to integrate that differential equation for 1/30th of a second. And it's not just, oh, well, just take the derivative and multiply by 1/30th. That would be a straight line increase. The reason why you have this e to
Actually,
ex thing is because it's going to be a ramping up increase.
Actually, I think that can work. I think that's the Euler version, and it works for small delta t. Works better for small delta t than large delta t.
Yeah, and so in this case, I think what we want from a dynamics perspective is to not assume that delta is so small that all of the second and third order effects are completely ignored.
Mm-hmm.
And that's why you get this A bar isn't just K times A. That would be a very simplistic thing. Instead, you have this e to the some constant C times A. Or in this
Mm-hmm.
case, that constant's called delta. So in S4, when you train the model, you learn what that good constant is. Just like if you're doing that high school math problem about the multiplying bacteria, you have to learn what the right constant is. So if I recall, like if you just have something that doubles every hour, if you were doing 2 to the whatever, then K is 1. But when you do e to the whatever, because you're now doing e to the whatever instead of 2 to the whatever, right, you end up getting ln of 2 or 1 over ln of 2, I can't remember which, as your constant. But even if you don't remember the gory details, I don't remember it perfectly. That's essentially what's happening here is we're saying, and then you can imagine, like in the extreme, if instead of 1/30th a second, what if we wanted to sample it every 10 seconds? You're really not expecting linear dynamics here, right? But just to be clear, taking a continuous function and trying to estimate it for discrete time steps is not quite the exact same thing as sampling discretization. So when you have a CD, it's not analog audio, it's discrete, and you have 44,000 samples per second. Those, to my knowledge, are just instantaneous samples to the best of the ability of the microphone, to pick it up. It's not really trying to estimate anything about what happened during that 44,000th of a second. It's just saying, boom, I took a measurement, boom, I took a measurement, boom, I took a measurement.
Yeah,
So
the difference is,
that's A to
you're
D,
starting with,
but yeah, go ahead.
oh, I was just going to say the difference is in that example, you're starting with the function as opposed to the differential equation here. Here we're starting with the derivative, and so we have to do the estimation.
Right. So we're saying we have a closed form derivative and we want to do the estimation. So this is a little bit different from potentially, I think the question was like, are we using discretization in the same sense? So we're not using it in the sense of A to D, analog to digital discretization, okay? Because that means just sampling in my simplistic mind. This is integrating a closed form differential equation in order to create data points 1/30th of a second apart, let's say.
Practically,
Mom and Dad. Background there.
Welcome back. I'm Chief Meteorologist Jim. We're ready with a quick look at your weather forecast. We are tracking atmospheric river just off to the north. That's going to bring the heaviest rain near the California border.
Do it, Jerry.
Huh? I'm looking for it. Who is it?
Henry Kendall. Or can we at least mute him?
Yeah.
Thank you, Henry.
Practically speaking, that's the part HT is equal to a bar HT1 is that's RNN, and when we plus the b plus b bar xt, it means that we are considering whatever it has before that. Is that right?
B bar is the input signal, or B bar times xt. Xt is the input signal.
Right. Yeah. The whole context in.
Ahmed, can you turn up your microphone a bit if possible?
So Ahmed, as you were sharing your comment, I was posting a picture on the chat there where it apparently shows exactly using the backward Euler method and speaker iteration that this is actually related to RNN. You can take a look at it offline if you want to, but your intuition is spot on.
Thank you.
Okay. Are we, should we get back on here then? Where were we? So we computed A bar and B bar. We also computed C, which maps back out from the internal state out to the inner, what they call, it will end up calling inner, essentially to the X. And then there's another, this is the residual. So it's residual, this is residual in a layer to input to output perspective. So the input has come in through the projection, the conv, and it will be passed forward past all this stuff that's going on here in the state machine and be added to the output of it. This is a parameter. So I always thought of residual as being like a constant, but what happens here is they initialize, I believe, the D to the I vector, so ones on the diagonals. But then they mark it as a parameter, much like over here, they generated a log, but marked it as a parameter. Whether they tune it all the time or they just fix it and then maybe unfreeze it when they want to do fine tuning or something, I didn't detect that, but I was surprised to see both of those be parameters. Then there was one other part that where they're taking the original model input, they're running it through a projection to the same dimension actually as this one. They're labeling this the Z vector. It also runs through a nonlinearity, and they're using that to modulate the output. So there's both the C and the Z that modulates it. So that's different than state machine. That I think actually, does that even show up on? Yeah, okay. That shows up on the larger figure 3 diagram where they're doing this modulation after the state machine. I don't remember us talking about it much, but okay. So that is what I got out of looking at the code. Are there any questions about that? Any clarifications? I tried to use the notation. These purple things are just operations functions. The green ones are all learned parameters, and the blue ones are calculated or vectors. B just represents a vector. And then the operations, plus is an element-wise plus, times an element-wise times. And the O's are, so they use heavy use of einsum, which I didn't have a lot of experience with, but it's a way of doing operations. It's kind of like, if I understand it, well, it handles a lot of different complex dimension tensor mathematics. Usually, I think kind of dot products on some dimension. So you multiply 2 dimensions and sum them up, and that replaces that dimension. But they also do dimension swapping and all sorts of things. So some of these I couldn't quite capture as, in a way, this operation here was more of an outer product between the output of the DT projection and the beam matrix, for instance. So I just put in O where it was that type of operation that I couldn't describe with one word.
So Roger, one other thing that you helped show me earlier this week is even if we were talking about just a single floating point number scalar input, right? One of the things that happens is at the bottom you have those input projections. So let's say that increases it to 8-dimensional in our sort of hidden space, our state space, right? All the stuff that's happening, that complex stuff with the A's, B's, and whatnot, is happening individually for each of those 8 channels.
Mm-hmm.
And there's no mixing across the channels. The one place where there is this cross-channel thing is that part that you had mentioned and I had first spoken up. So the DT proj, the thing that you called DT proj. Okay. So you have your input, and because this is Mamba and we let things change, then you run it through a single layer. You can think of it as an embedding, you can think of it as an MLP, you can think of it as a projection, whatever, to calculate the actual B you're going to use, the actual C you're going to use. And then for delta, what they decided to hard code an inductive bias. Okay, so what happens here is they only calculate one delta. Even though they have 8 channels of data, they only calculate one delta. And then let's say that is 0.9 or whatever. Then they use 0.9 across all 8 channels. They do not let each channel have its own delta. So everything else is just channel-wise. They're all acting independently, completely ignorant of each other. Delta is the one place where that's not really what's going on here. So that's what that delta and soft plus thing is doing there, Roger.
Yeah. So, right. So there's a difference in the dimension here, the state dimension versus they call this the D inner dimension. The inner dimension is what we saw in the first slide that went across that you were using, Ted.
Yeah.
We saw the inner dimension, and then the state dimension was the 4 lines across the top. So this one's bigger than this one. Yeah, and your point is right that they essentially all those 4 lines will be switched at the same time. The DT will be used for all 4 lines or n lines, whatever it is.
Right.
There is, however, so the state going through here, the A matrix, A bar matrix, is a diagonal matrix. And so the state, there is no interaction between any of the states going across this way. So the 8, I think you used the example of 8. There's 8 times more channels here. They called it an expansion factor, I think, at one point. All 8 of those are running completely independent. The dynamics controlled by the single diagonal matrix A bar. But so that's in the time dimension. But as you go vertically in the layer dimension, there should be mixing that can happen both at that level and presumably at those levels. These seem to be full matrices from what I could tell. So you can so in time they're independent, but between layers they're allowed to blend those states, crossover, whatever. And you and I, Ted, hypothesized that independence of that, one of the advantages of the independence would be that you could run, since in Mamba, the hardware optimization means do an entire time sequence on a few of the states rather than doing it all at once. And it may be that independence of the states would allow you to do partial. Now, whether or not they're actually doing that, we don't know, but they could do a part of that vector, sweep it through time, the next part of it, sweep it through time, etc. Because A is diagonal.
Yeah, like if my there's so many dimensions, it gets really confusing. But like if my input is a certain size and I've got so many token positions, and then in addition to that, what we're talking about is this state space
Expansion.
as an 8 times expansion. Okay. Because all of those are independent, if I can't fit all of that into my GPU at once, what we were talking about, Roger, is you can safely split that 8 in half into two different 4s, and you don't need to do a third calculation where you mix the results from each of the 4s. You just split it and you're done. And if that doesn't fit in memory, you could split it into 4 chunks of just 2 each, or whatever you need to do in order to get it to fit into your GPU core to do the math, because they're all acting independently. You're totally safe. There's never, it's like if you know how like matrix multiplies work, if your GPU actually is multiplying 64 by 64, I don't know what the chunk size is, but your matrix is actually much bigger. It's 1024 by 1024. And so what's 1024 divided by 64? I don't know. Is it 32 or whatever? I don't know. But like, you can't just do 32 times 32 calculations. You're doing way more than that, because you're doing the, like pairwise ones, and then you got to mix them together where like, the rows and columns overlap. So you're doing way, way, way more. But for this, when you keep all of those channels separate, then that means that once you've calculated a channel, you're just done. You don't have to worry about any of the other ones.
So I'm going to pick up the pace a little. We're getting at 7:40, and I can't continue next week. So I want to try to push to get through this. So this, we've covered some of the later stuff, so I think we're probably still okay. But anyhow, so here I just added the dimensions as it appears in the code. And you can see you come in with a model dimension, which gets projected into inner. Inner is the part that we saw before, that X is kind of the inner dimension. The inner dimension comes up to this X projection, which goes into 2 levels. D state is the size of this red vector, the state vector that goes through. DT rank is small. I think it was like 1/16 of D inner, something like that. So it goes down into a small dimension and then projected back up into a full D inner.
It's 1/16 of the D model, but yeah, go ahead.
1/16, okay. The A matrix, of course, has to be D state wide because it's a diagonal matrix by the size of the state. And the expansion, I'm not sure. Do you know what? I think the default expansion was like 16, I think.
Even or 2. Default expansion was 2, but I mean, it doesn't matter. It's a parameter to the.
I think that was down here, but for the E, well, anyhow, the state dimension is larger. A is diagonal matrix on that. C, there's an operation here between the C matrix and the state dimension that generates a inner size, D inner size, where you add your residual connection. Was there a question?
Are you sharing something that's we don't have it? If
Oh, you don't have my display right now?
Yeah, I can see Roger's screen. Did your Zoom act up?
You might want to, maybe pop out and come back in or something. I don't know. It should be.
That's okay. That's okay.
Okay.
I got you, and I got your mouse too.
Okay. So yeah. So the C is the one that takes us out of the hidden state and brings us back into this D inner with the equivalent of the X. And then there's this modulation against. I think the modulation was a element-wise modulation. And then we project back out into the D model. I tried to include over here, so there's going to be 2 methods that we'll look at given the time. I didn't finish this algorithm 2, all the terms in algorithm 2, but tried to map them to the internal source code dimensions. And then in the internal, we're going to look at a step function and then a forward function. In the step function, these are the einsum representations of these different matrices. You can see that in the forward, they deal with L appears, which will be the sequence length. In the einsum step, which is used for inference just to predict the next token, you got the dimensionality, but you don't have the length of the sequence as part of it. I found the code a lot easier to read in step, so we'll go through that. But the forward is basically the same flow. It's just dealing with the length of the sequence more. Some places you can calculate things combined in one example and not in the other. They also, in the forward method, they reorder things so that the length is the last dimension, because that's what they call the fast dimension, because they're running through the lengthwise on the sequence, one element at a time running through. So that was one other difference between the two. Okay, so this is Einsam. If you're not familiar with that, take a look at that, and it helps read. Vita, you had a question.
Yes, hi.
Hi.
I have some comments about the previous picture.
Sure.
Yeah, so here, actually, I mean, the paper is a bit confusing because, they talk about per dimension, they increase it to n and stuff like that. But then, of course, in the code, they do things in parallel, right? So they use matrix multiplications and matrix operations to deal with all of those n dimensions associated with the d dimensions all at the same time, right?
Yes.
So the output of a bar, for example, here, I mean, the red line that you have for a state, state is not d state. State is d state by d inner. It's a matrix. It's not a vector.
Well, we can look at that when we're going through step, the function step.
Even there, doesn't matter. All of these, I mean, the whole reason that they talk about this thing, that they do everything in the GPU, using the shared memory and stuff like that, is because they are dealing with d state by d inner matrices. So, like everything is multiplied by d inner. The dimensions are multiplied.
Right.
So,
whoops, sorry. Yeah, so down here where the state where we're representing it is the dimensions are
exactly. So then okay, so what you have in that table is correct, definitely. But then in the picture, when you say, you have d state on top of the red line, everywhere that you have those red lines, or above it, you have only d inner. I mean, those are a little bit not correct and doesn't match your tables. I think your tables must be right. Yeah. But then, yeah, the A bar is a matrix. Yeah, I mean, in their code, A bar is a matrix. The state is a matrix. But of course, in their paper, they talk about everything in terms of what happens to individual bits of state. So, there's that disconnect. But yeah, your tables are fine. Yeah, I just, I thought maybe, there's some, misunderstanding or something. So I just wanted to say that. Hopefully it's helpful.
Yeah. In here, we're, so what you're saying is really the state.
And you were right. Some of those operations, those Einsam operations that you have there, they actually do auto product. So that's how you get a D state and a D inner, for example, at the output of B, right? So if you look at the B, the output from B goes to this Einsam, and so B is D state, and then you have this from the soft plus, you have the inner, then B bar becomes a matrix because there's an auto product that is happening here. And then some other places there are auto products too. It's it's like tricky, but yeah.
Yeah, let's do this. We just got 15 minutes, so let's do this. Let's go look at the code.
I'm done. Yeah.
Yeah, we can just see what it's doing there. So I think, let's see, where do I have this? Okay, so the two things we're going to look at are the Mamba simple, and then there's selective state update. So in here, they're defining the Mamba. They have D state, the model as one of the inputs, the expansion factor, the conv is how wide that time series 1D convolution is. We can see that the inner is the model expanded by some number. So I guess that's down in those original projection models. So yeah, here's the in projection we saw down in the two trapezoids down. The model goes from model dimension up to inner dimension times 2 because they split it. The con 1D is in the inner dimension of D inner. The X projection is the one that is used to calculate B, C, and DT. So it takes whatever the inner dimension is and generates something that's got rank and 2 D state sized. So this is the dimension of the state size one. And then they project that rank back up to a D inner size. So they kind of compress it through this bottleneck of DT rank.
And super quick, the only reason why there's a ×2 on the line above is because they're doing B and C at the same time, just for performance improvement. It really would just be a single state if it was 2 lines, but it's obviously faster to do it in one.
Yeah. Yep.
Pass.
And then here's that ST4 stuff that I was talking about. It's just 1 through N for A, and then they take the log of it because they want it to I don't know if they want it to be in log space or if it's because they want it to always be positive. I've heard that description twice or different times, but anyhow, they take the log of that diagonal, and that's what they use. I think what this is saying is that's what they use to initialize the parameter a log. Anybody else have any insights into that? Does that sound like the right interpretation?
Yes.
Okay. And then D, which is the skip parameter, they initialize again to be, it's on the D inner size, so they initialize that with 1, so it's just an I matrix. But they do make it a parameter, so it seems like at some point at least they're able to tweak that and learn it. And then the out projection, they just go from the inner back down to the model size. A linear projection. Okay, this is the forward one. This is what you'd use in training. There's a bunch of stuff in here, but I'm going to skip forward to the step just because it's a little easier to read. This is the step, and this works with inference. It'll do one at a time, is what I understand. I think that's what it's saying. So it takes the hidden states from the prior predictions and the con state, because remember that was the other one that flowed through time, that convolution that was down at the bottom. And then whatever this would be that state, the red line that was. Actually, no, I think this is the red line. I'm not exactly sure what that one would be. So this is the projection down to the bottom that gets the X and the Z, tying that back to, that's these guys down here. So this is the X and that's the Z. And then if we have a convolution, they run the conv here, I believe. This, I think, is, you can do it in a fused kernel type of thing, but it's equivalent to this. They do that in a few places where they'll do either a fast way or a slow way. And then they run it. There's the activation that you see. That's after the this is the convolution that stretches out both sides, and then the output comes through this nonlinearity silo. Okay, so here we do the XT projection into, again, they do it one projection because it's faster with this rank D rank plus 2D state, and then they split it out into these guys, BC. Let's see, this is the second little one. I don't know why they just do it this way. It's linear projection using those weights. So that, I believe, is this guy here, the DT proj, doing its work. And then they're expanding this parameter that's a log, running the running the EXP of that to expand it back, and then they take a negative of it. So we're guaranteed that this is positive. So because of the minus sign, we're guaranteed that A is negative, and that would be A for the continuous model. And then we have to go through, and we will. Here's a fast way to discretize it, or we will do it. Here we're able to see what's really going on. So they compute the dt as the soft plus of dt. That was that step right out of that soft plus right after that dt projection. The discretize A is the dt times A to the e to the exp of dt times A.
So this is so line 241. If you look at the outcome, it is BD, and I think that's what Vida was saying. This is DN BD comma DN to BDN.
DN so it should have been yeah. I'll update that. Okay, and so here's something where it seems like they're doing this different than the paper, because B is just being computed as dt times B, so just the final term. If you remember, in the paper, they had this full expression, but in the code, they don't seem to do that. It seems like they did a little shortcut. And I think that would be the Euler, the equivalent to the Euler.
Yeah, I agree with you. So, sorry to interrupt you. So in the paper, sure. They have the, this other more complex expression for B, and that is the correct one. That's the accurate one if you do the math right. But then if you do the Euler expansion, which doesn't have all the terms, it has only the first 2 or maybe 3 terms, then, that thing gets simplified and you'll end up with delta B. But then in the paper, like you said, they don't mention anything, and that's why their code is not quite matching their paper.
Doesn't quite. Okay, so you observe that, yeah.
Yeah.
Okay, and here's the magic state transition then, I think. This is the dA times the prior state. So that's the A bar times the prior state, and we're adding in the dB times X. So in the picture, we've got this is their X basically, and we've got the X bar, we're adding that into the D state times N. We're adding that together to update the state. Let's see, what do we do next? This is Y. Computing Y is this operation of the state and C. So it goes from this higher dimension dn back into D. And then we add in the residual path times A, add that in. And then we throw it through a nonlinearity here. And that's that nonlinearity act. Oh, act of Z, because, yeah, so you're taking your Z vector and running it through this nonlinearity and then multiplying that times the Y at that point.
I just want to say something quickly. This whole Z thing is not the residual connection. Actually, the residual connection is around this whole block, and you don't show it in the block in the diagram that you have. This Z path is a path that is kind of captures what they had in H3 or something, that is like the MLP block in the transformer that they are now in parallel to this and combining them together in this weird thing. So the residual connection is actually around the whole thing. They don't show it here.
Okay. Thank you for that clarification. Yeah, we had been calling it the residual, but yeah, you're right. That's where this MLP model that goes around. That's what you're referring to, right?
Yes.
Yeah, that's the gated MLP, the Z part.
Gotcha. Okay.
The thing I wasn't sure about is I don't know if you look at the code, I'm not sure that there is a residual connection around the whole thing. The part with the D, I think that's the residual connection.
So this is the, can you go, scroll up the function that this is in this part?
Oh,
I think this
in the
is a
code?
mixer. Is this a mixer or something?
Yeah, they call this the mixer. Yeah, and then
So there's the create block somewhere. So, there's these nested types of objects. One of them, which includes this in itself, that one has the residual connection.
so yeah, that was a little confusing. They start up here, didn't they? Oh no, they dropped this one. They don't even have D, do they?
No, for simplicity, they don't, but it really is in equation 1b. It's C times hidden state plus D times.
No, this is the dynamics. This doesn't have to do with residual connect. Oh, I'm sorry. Yes, you can say that in terms of the dynamics, you have some residual thing going on. It's not called residual really. It's just the input. But then, just like transformers, where in the vertical direction of the network you have residual connections, I'm talking about that residual connection. And
Yeah. So D,
one that you call residual.
So D is the residual. D is the residual. The Z then is the MLP.
Yeah, right. No. I think what Vida is saying is right. If you go to the code line number 143 to 150, you'll see that this whole Mamba block is surrounded, is part of this residual block, which includes RMS norm around
it. What line did you want? What line, Dave, did you want? Dave?
Yeah, sorry about that. So line 62 to 64, if you go there.
Are we looking at different files?
Probably.
Is it the
This is Mamba symbol.
It's the Mamba symbol. So in the actual Mamba,
yeah, it's not going to be in the init. It has to be in the forward pass.
Yeah. So Roger, maybe not. It's not that in the simple one, but in the actual implementation, even though it's not simple, it's called Mamba minimal. There's a model.py file also there. There they have, and I didn't know I was looking at that. Sorry. So Vida is saying is right that they have Mamba, which has a list of residual blocks, and the residual blocks is that is nothing but Mamba blocks and RMS norms in there.
So maybe this Mamba simple, Roger, is just one layer.
It is.
The one Dave's looking at is actual multiple layers. And then you have the concept, like with transformers, of the residual stream. And right. It's just each layer is adding to the stream.
I agree, although I would say this D is a residual within the SSM block.
It is.
There may be another one around it.
Roger, just for completion, if I just give you the file name and we can just go to line number 172 there and it will show there.
Okay.
Residual.
We're gonna have to talk about time management. So it's 8 o'clock.
We're at the hour.
Yeah, we're at the hour.
Roger, if you just click on that chat link, you'll pull up that file and it will clarify before we close the meeting.
The chat link on the bottom there, Raj. Yeah. Oh, there it is. What line was it, Dave?
Yeah, so if you go to line number 143, let's say. So this is the residual block, which is part of Mamba block. You have this chain of those. And inside, part of Mamba. And inside this, you have the Mamba block and RMS norm. But if you look at the forward, go to line 172. It's just one line of code, which is mix. Oh, you passed that. You have mixer, which is your Mamba block. And inside that is your norm plus X. So this is your residual there, plus X there.
So this is a residual around the part we were talking about here.
Yeah.
So there's a residual within it on the,
Yes.
when you're still in the D inner space, right?
Yes. Yes. So
yeah,
there are
we have it projected back out to the model space. And then there's another residual out at the model space when you wrap this Mamba layer. Because here we're just Mamba, right? When you wrap Mamba, you can wrap it with the residual, and they had a norm on the output of it and use that as a block.
Yeah.
So.
Yeah, that was a good Vida. Thank you.
Okay, so yeah, that especially that MLP, I had not correlated the MLP, hadn't thought of it as MLP. I'd forgotten that that was what they called it in the original picture. So, okay, anyhow, this is the project back out to the output. So this is a D model. What I haven't captured is then there's wrappers around that, which actually then changes. What I had done, let's see, was depicting that these, when stacked through time, each one of these would be a token. Ted, this is like your transformer one, right? Each one has a token coming in and a token coming out. And then you have state running through all of them. And you have this convolution that slides across all of them. And when you have a multi-layer version of that, it looks something like this, where you're computing through the sequence, and then your output goes to another layer. It mixes here, goes to another layer. It doesn't mix in time coming out, but then it comes up and mixes between the different dimensions, comes up to the next layer. And when you're computing, when you're training this, you would have a loss function at the top of each one of these that you would compute a gradient on that would propagate down and back through time on each one of these. I guess, can I say back through time? This is kind of an unrolled RNN, right? And it would propagate down to the next layer and back through time on that. And it would add in at each token, add in some additional gradient to back propagate.
So I think if you did copy and paste a few more times, it would be more clear though.
Yeah, that's what I was thinking.
You want another 20 layers or something like that, Silly?
Well, to Vita's point, I'm not showing a residual on here, which I need to, and I'm not showing a norm between the layers. If we were to look at that, the full Mamba model, I don't know what they call it. What did you call that last one? What class is that? Residual block. Oh, that's interesting. They call that Mamba.
Well, that's the class.
Mixer sec simple PY under modules.
Okay.
Oh, sorry. What I'm talking about is in the main code base, not this one. Sorry.
Isn't this the main code base though? The Mamba minimal.
Oh, I ended up sending the link to the parallel implementation that someone else did. This is in John Ma's implementation. Yeah.
I have sent a link to the original code base where the residual connection to that line.
Oh, on the State Space's GitHub. Yeah, it's at the bottom. It's the last entry in the chat.
Okay. Yeah, and then Roger, when we do these diagrams where you see the different token positions, just know that that diagram is for us to understand conceptually how the different words, the different tokens get processed by the model. Neither the transformer nor Mamba is actually instantiating separate copies of them for each token position. It's just symbolic because your input matrix, instead of being a token, right, is L tokens. And so there's just a whole nother dimension to the input, okay? So if you think of just a transformer, you might think, okay, I have one token as input. If you think of a sequence, then it's L long. And then if you have a batch of things that you're processing simultaneously, then it's B times L, okay? And that's going to be true for Mamba too, that you're going to have this, B times L input, and each of them is model D. So you get this B times L times model D tensor. That's your input. And you just pass that big chunk into it. You're not actually getting L copies of your transformer or your model. But I just find it's much easier to have an intuition about what's happening when you unroll it and draw it out as if they were separate.
I agree. It doesn't fit on the paper well, but it does provide a different context. So yeah.
Rolling through time.
Okay, so we got through a couple, 2/3 of this anyhow. So I think one of the things that I was talking to Dave and Ted also about is how do we get rid of vanishing gradients was a big part. It was one of my big questions, but I think it ends up being a much bigger topic. So I'd like to do a Hippo talk at some point because there's a lot more we could dive into on that. And Jason's friend, I don't know if David's here, but Jason's friend asked the question about, I think we also had this came up in our meeting was, is there something magic here? Or if we'd known about this hardware acceleration, could we have done this back when LSTMs were hot? And I don't know if, I'm not sure.
No,
I think
we
this
can't.
idea that you don't mix channels is one. The vanishing gradient, I think you needed to solve that before you could do it. You might have been able to speed up LSTM, but if it's a vanishing gradient problem, I don't think you still would have had a problem. So, okay, let's go ahead and end it. We're 10 minutes over, so why don't we go ahead and end it on that?
All right, I'm gonna.
Nice job, Roger.
Nice job, Roger.
Yeah, thank you.
Thank you.
Great job, Roger. Thank you.
I do think
Very
handling Hippo
cool.
as a separate topic is a good suggestion.
Yeah,